Deep networks suffer from a version of the telephone game. As signals pass through layers, information is modified and distorted until the original input becomes unrecoverable. This dilution means that by the final layer, early layer features are practically lost to noise. Standard residuals act as a conveyor belt, adding new features to the existing identity. This creates a direct path for the signal. But because every layer has an equal weight of 1, each individual contribution becomes diluted as the network deepens. Because each layer adds its output into a single sum, the deeper we go, the more information gets diluted. Examining these layer contributions shows a clear pattern. The later layers naturally dominate the final signal due to their larger magnitudes. Here, the earliest features represent less than 20% of the total computation. This suggests that depth creates a bottleneck for original input clarity. Duality connects sequence and depth attention. Just as tokens look back through time, layers can now look back through the network. This math transforms horizontal context into a vertical search for better features. Attention residuals treat depth like a sequence, where each new layer learns a unique query to reach into the past. Instead of blindly summing every previous output, the model assigns keys and values to each preceding layer. These curved paths represent the scores and softmax weights that determine how much each layer actually matters. This transforms the residual connection into a learned, input-dependent retrieval system rather than a static conveyor belt. By projecting a query vector against previous values, we compute relevance scores for each layer. These softmax weights allow the network to skip the middleman, prioritizing the most useful signals through a weighted sum. This creates a flexible, learned highway, yet scaling this to hundreds of layers hits a physical memory wall. Depth creates a memory wall. Linear scaling with layers, burdens, pipeline parallelism as this old communication bottleneck forces us to find a more efficient way to aggregate information. We solve the memory bottleneck by grouping layers into blocks. Representing each block as a sum of its internal layers means we only store these summaries for attention. This reduces memory costs to the number of blocks while keeping the benefits of learned retrieval. Practical improvements in deep learning must translate to better scaling laws. Even as compute increases, the consistent gap in validation loss shows that block attention residuals effectively outperform the standard transformer baseline. This efficiency gain translates to a model reaching target performance levels using significantly less total compute, provided the training dynamics remain stable. Deep networks often struggle with exploding signals as we move through layers. In a standard architecture, these values accumulate and grow exponentially. However, block-based attention residuals solve this by resetting the sum at each boundary. This keeps the signal magnitudes bounded and stable, which is exactly why the training process becomes significantly more predictable and efficient. Attention residuals transform deep networks from a game of telephone into a selective retrieval system. This summation formula represents a fundamental shift. Layers no longer just pass messages, they query the past. By using blocks, we achieve massive compute efficiency, making depth work smarter.